All right, this is AP Chemistry Podcast 5.2, and we're going to start in Chapter 11. We're going to talk about properties of solutions, solubility, vapor pressures of solutions. So the first thing we're going to talk about are the different types of solutions you can have. Here it gives you a bunch of different examples, so air and natural gas. The state of the solution is a gas, the solute is a gas, the solvent is a gas. Important vocab that you need to remember, the solute is what's being dissolved. And it's usually the thing that's in the smaller quantity. So what's being dissolved is the solute. The solvent is what does the dissolving. I'm going to run out of room. What does the dissolving? And you can finish writing out that word. So you can see that solutions don't just have to be some sort of solid dissolved into a liquid or just two liquids mixed together. You can have gases. You can have a solid for a solution, so all your alloys. Your alloys are solutions. They're two or more metals mixed together. So there's a lot of different types of solutions that there can be. We just really focus, though, a lot on either a gas in a liquid or a liquid in a liquid or a solid in a liquid. Usually we are dealing with the solution that is a liquid. So most common is that, but you need to be able to realize that there are a bunch of different types of solutions. Okay, there are different ways that we can express the concentration or the composition of a solution. And what we have here are the 4 different ways that you'll be responsible for knowing. Molarity is the most common, I would say, because it's also called concentration. And it's just a really common way that you can see kind of how much solute you have in your solution. So for example, with the acids that we're going to make, maybe you know that they're 0.2 molar or 5 molar or 0.001 molar. All those tell you how concentrated they are. So molarity is the way that we can tell how concentrated they are. Another composition calculation you can do is mass percent. That's where you take the mass of the solute divided by the mass of the solution and you multiply by 100. Mole fraction is one that we used a little bit in partial pressures, but here it is again. That's where you take the moles of whatever you're looking at. So whether it's the solute or the solvent, the moles of whatever you're focusing on divided by the total moles in the solution. And then molality is not used a whole lot, but you still need to be aware of it. It's little m, molarity is big M, and molality is moles of solute, just like molarity, except it's per kilogram of solvent, and this is liter of solution. So there are some key words here that you need to be aware of so that you know what value to put on the bottom or the top when you're doing these calculations. So we have our first example problem, and it's a long one because they're asking us to calculate the molarity, the mass percent, mole fraction, and molality of the solution that they're telling us about up here. So I'm going to do these one by one. I'll erase my screen after each one because there is no way I'm going to be able to fit all this onto one screen. So it says a solution is prepared by mixing 1 gram of ethanol with 100 grams of water to give a final volume of 101 milliliters. Calculate the molarity. That's where we're going to start. So the first thing we need to remember is molarity is moles of the solute over liters of the solution. So the first thing I need to figure out is how many moles of my solute I have. And the solute in this case is the ethanol. So I start with the 1 gram of ethanol, and I do quick stoichiometry. I just use the molar mass that they gave me. I don't have to add it up. So 46 grams is 1 mole. And when I do that, I take 1 divided by 46, and I end up with 0.0217 moles. And that's of ethanol. The liters of my solution, I have to take the 101 milliliters and just convert it to liters. So I'd bump it 3 places back. So this would be 0.101 liters. And then all I have to do is just plug it into my molarity calculation. So big M is equal to 0.0217 moles of ethanol divided by the liters of my solution. And I come up with an answer of 0.215, and we label it big M, molar. make sure you don't do MOL because that's moles, it's not molarity. And there's a difference, and I always see students doing the wrong way. So moles per liter, and then this is molarity, or molar is how you would read it. Not MOL over liters. That would be incorrect. So make sure you're labeling correctly. So that was the first one. That was molarity. The next one we're going to do is the mass percent of ethanol. So our equation for the percent by mass is the mass of ethanol, and I want to divide that by the total mass of my solution and multiply by 100 to make it a percentage. So the first thing I need to figure out is the mass of ethanol, which I was given in the problem, so I don't have to worry about that. They also gave me the mass of my water, so to figure out my total mass is just a matter of adding up the two masses together. So I actually can just plug this right in. So percent by mass is going to be equal to the ethanol, because that's what I'm focusing on, divided by those two added up, because I want the total mass on the bottom, and then I multiply by 100 to make it a percentage. And when I divide all that and multiply by 100, I get 0.990%. So in terms of mass, that's how much of the mass is made up of ethanol. Oops, wasn't finished. All right, continuing on. So we've done molarity, mass percent, now we're going to do mole fraction. So the mole fraction of ethanol is equal to the moles of ethanol divided by your total moles. So again, I'm going to have to figure out how much ethanol I have in moles. And we already did that for the molarity calculation, so I'm just going to recopy that down. So we had 0.0217 moles of ethanol. And then the other thing I need to figure out is my moles of water, because I need to be able to add them up to find the total moles. Let's see, water is 100 grams. That's what I have. Water's molar mass is 18. So when I do that, I end up with 5.56 moles of water. So then to calculate my mole fraction of ethanol, I'm going to put the 0.0217 moles on top, and I'm going to divide that by the total moles, where if I added those up, it would be 5.58 moles. And when I do that, I get 0.00389. There are no units on mole fraction because those moles go away. You're left with just a number. So no units on mole fraction. The last one we're going to do is molality. And molality was the little m. It was moles of the solute over kilograms of the solvent. So again, I need moles of solute. We've already calculated that. So my moles are going to be 0.0217. That's for the ethanol. We've already done that calculation twice now. And then the kilograms of water, because that's the solvent, I have to take the 100.0 grams and convert that to kilograms. So I move the decimal over 3, and I end up with 0.1 kilograms. So then I just plug in to the molality equation, 0.0217 moles divided by my kilograms, and I end up with 0.217. This time I label it little m, which if we were reading it, we would say that this is 0.217 molal. So molal and molar, little m, big M. Make sure you don't get them confused. All right. Let's see, now we're going to talk about how do we get solutes to dissolve in solvents? How do we know if they're going to go or not? And the big thing that you're going to hear is like dissolves like. So polar solvents, say we have water, is going to dissolve a polar or ionic solute. So if you have something that's polar, it's going to dissolve something else that's polar. Your nonpolar solvents are going to dissolve nonpolar solutes. So like dissolves like. And then here's a little cartoon to kind of help you out with that. Okay, when things are dissolving, they go through 3 separate steps. The first step when we're doing this is we want to separate the solute into its individual components, and that's called we're expanding the solute. So we're making space in the solute for the solvent molecules to come into it. The next step is overcoming the intermolecular forces in the solvent to make room for the solute, and this is called expanding the solvent. So number 1 was expanding the solute, making room in the solute, separating it into its individual components. 2 is dealing with the solvent, where we have to make room for the solute to come in. And then the third step is allowing those 2 to mix and allowing the solute and solvent to interact to form the solution. Those are the 3 steps when we're talking about how liquid solutions are formed. And here's a picture of those 3 steps. So here's your separate solute and solvent. You have to expand both of them, and then when they mix together to make the solution, that's the 3rd step. Each of those steps has their own delta H value. So delta H for the first step, delta H for the second step, and then delta H for the 3rd step. If you add up each of those individual delta H's, you get the delta H for the solution. So that's where we can see, is it favored for the solution to be formed? Things that you should notice is that steps 1 and 2 are usually endothermic, and that's because, even though it doesn't really look like that, so they're usually endothermic because we have to put energy into the kind of process to overcome those forces and bonds. Step 3, where those 2 mix, is usually exothermic, so energy is released. The enthalpy of the solution is that delta H of the solution. Again, add up all the individual steps to get there, and then you can tell if it's positive or negative. So we have an example problem here. It says, explain why water and oil do not mix. And then in your explanation, they want you to use the idea of delta H and delta H for those individual steps. So the first thing you want to look at is delta H for water. Delta H for water, if we remember water, has hydrogen bonding. So because hydrogen bonding is a pretty strong type of an intermolecular force, that means it's going to have a pretty large, delta H value for the water. It's going to take quite a bit of energy to separate the water to expand it in what we call that first or second step. The same thing is going to be true for oil. Oil has London dispersion forces, but oil has very long chains. So remember when we said that the longer or bigger your molecule is, the greater the London dispersion forces matter? Well, in oil, they play a really big factor, and they're actually pretty strong. So again, in this case, because we're dealing with strong intermolecular forces, we're going to have another large delta H value. So we'll call this delta H1, delta H2. It doesn't matter, you can switch them. Then if we want to think about the formation of the solution, so formation of the solution, delta H of the solution. Water and oil don't like each other because one is polar, water is polar, oil is nonpolar. So they're going to have not a lot of interaction going on, so they're going to have small interactions. Which means that our third delta H, oops, this should not be that. That should be delta H 3 of when they mix. Very small interactions means that delta H3 is going to be very small. So if we're having a really big delta H1 and a really big delta H2, and then delta H3 is very small, then what we end up with this is a really big positive number. And big and positive means we'd have to apply a lot of energy to get this to happen. And that's why this is not a favored mixture. That's why we don't see them mix. That's why they settle out. because to separate the two different, the solute and the solvent, takes a lot of energy, and then the interactions that they would have, if they have any at all, are very small. So delta H3 is very, very tiny, which means overall this is not a favorable mixture. They're not going to mix together because delta H is so big and positive. And this is a table that summarizes what we were just trying to talk about there. You can see all the different kind of, I guess, polar, nonpolar combinations you can do for solutes and solvents. You can see what the delta H's would be, and then overall what would happen. So would the solution form, would it not form? And you can see that anytime delta H of the solution comes out large and positive, no solution is going to form, and that's why we were getting no solution in that example problem that we were just doing. There are some factors that can affect solubility. There's 3 different factors. So structural effects, pressure effects, and temperature effects. The structural effects were what we were just talking about. That's polar, nonpolar. Solubility is favored if the solute and solvent have similar polarities. That's the like dissolves like. That's what we were just talking about. We're going to discuss, though, pressure effects and temperature effects on solubility. So the first one is pressure effects. Pressure has little effect on the solubility of solids and liquids, but it does greatly increase the solubility of gases. So if you increase the pressure over a saltwater solution, it's not going to help you get more salt into the solution. But if you're trying to dissolve some gas into a liquid, in that case, increasing the pressure over it is definitely going to help your chances. So the pressure affects trying to get gases into liquids. And we can calculate that and see that effect using what's called Henry's law. And here's Henry's law right here, C equals Kp. C is the concentration of the dissolved gas, and the concentration will come out in molarity. K is a constant of that particular solution. It'll be given to you, or else they'll ask you to find it, but usually it's provided for you or it's in a table. P is the partial pressure of the gas solute above the solution. So P is the pressure above the solution, and as we change that, so you can see as P would go up, so would the concentration of the dissolved gas. So they're directly proportional, and that's what it's saying right here. This is only true when there is no reaction between the solute and the solvent. So this only works when you're trying to dissolve a gas into a liquid and there's no chemical reaction going on. You can't use this if those two things are having a chemical reaction. It won't work. We have an example problem here with this. So it says a certain soft drink is bottled, so that a bottle at 25 degrees Celsius contains carbon dioxide gas at a pressure of 5 atmospheres over the liquid. Assuming that the partial pressure of carbon dioxide in the atmosphere is 4.0 times 10 to the negative 4th atmospheres, calculate the equilibrium concentrations of carbon dioxide in the soda both before and after the bottle is opened. And they've provided us with the K that we're looking for here. So we're going to be using Henry's law, what we just talked about. And what we're going to do is we're going to calculate a before and an after value for C, because we want to know what's the concentration before I open the bottle and what's the concentration after I open the bottle. So before I open the bottle, C is going to be equal to 3.1 times 10 to the negative second, so I plugged in K, times the pressure they gave me, and because this is in atmospheres for the constant, I need to double check that my pressure here is also in atmospheres, and it is. So I would multiply that by 5 atmospheres. The atmospheres are going to cancel, which will leave you with moles per liter, which is good. That's what I need for concentration. So when I take those two numbers and I multiply them together, I get 0.16 moles per liter. That's the concentration of the dissolved carbon dioxide gas before I open the bottle. After I open the bottle, the carbon dioxide concentration is going to be equal to the same K value, but this time atmospheric pressure for carbon dioxide is 4.0 times 10 to the negative 4th atmospheres. And when I multiply that out, I get a much smaller number at 1.2 times 10 to the negative 5th moles per liter. So before you open it, after you open it, You can tell that that large change in concentration, that shows you why soda is going to go flat after a while when it's been left open, because it comes to a new equilibrium concentration, which is much lower than it was when it was bottled. All right, and here's just another picture showing you how the increased pressure will increase the amount of gas that's dissolved. So here we have our first equilibrium. The amount, I guess, of gas right here that's dissolved in the solution is a lot less than you can see over here. As the pressure is applied, more of these gas particles are being forced into the solution. So you can see how the concentration will go up as more pressure is applied to the situation. So that was the effects of pressure on solutions. Here's the effects of temperature on solutions. When we're talking about solids in water, generally an increase in temperature, so if we heat up the solution, is going to allow us to dissolve more solid into the water. So generally an increase in temperature increases the solubility of a solid in water. If I'm heating up water, I should be able to dissolve more salt into that water because the temperature is increasing. There are exceptions to this rule though, and it's very hard to predict just by looking at what the compound's formula is, whether or not it's going to follow this rule. But in general, solids become more soluble as the temperature goes up. The opposite is true for gases. Generally, an increase in temperature when we're talking about a gas going into water decreases the solubility of a gas in water. So as you up the temperature in a solution, you're going to decrease the amount of gas that you can get to dissolve into that water. Here is a table that shows you the solubilities of several solids as a function of temperature. So this is what happens to their solubility as we increase the temperature. And you can see for everything in blue, their temperature, as the temperature goes up, their solubility also goes up. So sugar, potassium nitrate, sodium nitrate, potassium bromide, everything in blue here. There are a couple here, the ones that are in red or pink, I'm not sure what color it looks like, or purple. They will decrease in solubility as temperature goes up. So remember, there's no key thing you can look for. That's just more of a trial and error type thing. Although most solids will become more soluble as you heat up the solution that you're trying to put them into. Here is the same thing but using gases. So here's your solubility up the y-axis, temperature along the bottom. As the temperature goes up, you can see that for the gases, their solubility goes down. So, opposites. An application of this is the Lake Nyos tragedy. In 1896, a large cloud of carbon dioxide gas was suddenly emitted from the lake. And then scientists believe that the lake suddenly turned over. And then they asking, how did this happen? So what we know about this lake is that the lake is a crater lake. So it's very, very deep, and it's sitting on top of a dormant volcano. So this really, really deep lake means that, and because it's in a tropical atmosphere, you get a lot of warm water at the top, and it just gradually gets cooler as it goes down. So cooler, and then we get really cold water at the bottom. So warm kind of makes its way to cold. And these rarely mix because most tropical lakes, they don't get a mixture of the different layers of water. They stay how they are. What happens though is that they found that these colder waters down here, because it was sitting on top of that volcano, it started to absorb a bunch of carbon dioxide gas. And because it was so cold and the pressure is so great at the bottom of this lake, we know that as the temperature drops and as the pressure goes up, that you can get a lot of gas into these colder waters. And it was the CO2 gas that was being dissolved into the really cold waters at the bottom. After that, though, so it just kept building up and building up and building up. Eventually what happens, and they're not quite sure what triggered it, but they think maybe it was the monsoon clouds or wind. It cooled the warm water on top to the point that it caused the lake to kind of flip over. All this cold water at the bottom flipped to the top and the warm water flipped to the bottom. So it did this kind of turnover thing. And when all that cold water came up to the top, all that CO2 was released. And you can see what happens is as that CO2 was released, because it's more dense than air, it just kind of made its way down these little hills and valleys, and it ended up suffocating thousands of people and livestock before they even knew what happened. It was just this plume of CO2 gas that just barreled down the hill, and it just suffocated a bunch of people. And now that scientists are monitoring it at the bottom of the lake, they are watching these carbon dioxide levels just really go up quickly. They're going up and up and up, and they're trying to figure out some ways that they can prevent this sort of tragedy from happening again. So they're trying to determine a way that they could pump out the CO2 so that when the lake does turn over, because they know it's going to turn over again, the amount of CO2 released is not enough that it's going to have this great effect anymore of suffocating and killing so many people. All right, vapor pressures of solutions. So liquid solutions have different physical properties than that of the pure solvent. So if we're looking at water versus salt water, this is why we add antifreeze to a car's cooling system, or we melt ice on sidewalks and streets by spreading salt. When we add in a solute that is non-volatile, so that means like salt, salt's not going to add vapor pressure. It changes the physical properties of the solvent that it's added to. So we can actually calculate how the vapor pressure will be affected. A non-volatile solute, like salt or sugar, something that doesn't go to the gas phase, lowers the vapor pressure of a solvent, and that's because it interacts with the solvent and it traps some of the solvent that would normally escape into the gas phase. It keeps it in the solution. So the vapor pressure drops because you get less of those molecules escaping to the gas phase. And this is using Raoult's law, and here it is. The pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. So what we're going to see here is as the mole fraction of the solvent goes down, so as you add more and more of the solute, then you're going to see the pressure of the solution also go down. They're directly related here. So we're going to do some calculations with that. And here's just another example. If the mole fraction of the solvent is 0, we don't have any solvent, then the vapor pressure will be 0 because our solute doesn't have a vapor pressure. But as we steadily increase the mole fraction of the solvent, we see that the pressure of the solution goes up and up and up, and to the point where if it's just the pure solvent, we know what the vapor pressure would be. So you can see as the mole fraction of the solvent increases, so does the vapor pressure. Our example problem says, calculate the expected vapor pressure at 25 degrees Celsius for a solution prepared by dissolving 158 grams of common table sugar, which is sucrose, in 643.5 centimeters cubed of water. At 25 degrees Celsius, the density of water is 0.9971 grams per centimeter cubed, and the vapor pressure is 23.76. Oh my goodness, they gave us a lot of information. But we can do it. So the pressure of the solution, this is just the formula that we learned, is the mole fraction of the solvent times the vapor pressure of the pure solvent. So I just need to make sure I have both these values so that I can plug them in correctly. I know then that I already have the vapor pressure of the pure solvent. They gave that to me right here. So this 23.76 torr is the P0 of the solvent. What I need to calculate then is the mole fraction of the solvent. So the first thing I'm going to do is I'm going to find the moles of sugar. And the moles of sugar, I started with 158 grams of sugar. They gave me the molar mass of it. So 342.3 grams is 1 mole. And when I divide those out, I get 0.4616 moles of sugar. I need to do the same thing for the water so I can calculate the mole fraction. So for the water, they told me, let's see, that I had 643.5 centimeters cubed of water. Because they gave me a volume, they had to give me the density so that I could convert to mass. So 1 centimeter cubed of water from right here is 0.9971 grams of water. And then I want to take one more step and use the molar mass of water. So 18 grams of water is 1 mole. And when I calculate that out, I get 35.65 moles of water. So now I have my 2 mole amounts, and I can go ahead and I'm just going to plug this all in together. So I have the vapor pressure of the solution is going to be equal to the mole fraction of my solvent. The solvent is what does the dissolving, which is the water. So I'm going to put the 35.65 moles on top, and I'm going to divide by the total moles, which would be 36.11. If I were to add those two numbers together, that's what I would get on the bottom. And I want to multiply that by the 23.76, which is the vapor pressure of the pure solvent. That's in torr. My moles are going to cancel. I'm going to be left with torr, which is a unit of pressure. And when I do that, I get 23.46 torr. And you can double check. I should get a smaller number than this because we have added some solute to my solvent, so the vapor pressure should go down, and it did. So your final answer for that one is 23.46. Okay, it does matter if the solute that you add will split into more particles. And what I mean by that is if you think about your ionic compounds, so we're talking ionic solutes here, the lowering of vapor pressure depends on the number of solute particles present in solution. In that problem that we just did, we were using table sugar, and table sugar is a covalent compound, and that molecule will just stay as one molecule. It won't split up anymore. But if I added sodium chloride, we know sodium chloride, when I put it into solution, splits up into sodium and chloride ions. So for every 1 mole of sodium chloride I put into the solution, I'm really putting in 2 moles of ions or particles, which is what I care about. And the same thing will be true here. For every 1 mole of magnesium chloride that I put in, I produce 1 mole of the magnesium ions and 2 moles of the chloride ions. So you need to pay attention when they give you those ionic solutes, because they do have more of an effect because they split up into more particles when they go into solution. So our example problem using ionic solutes is right here. It says, predict the vapor pressure of a solution prepared by mixing 35 grams of solid sodium sulfate with 175 grams water of 25 degrees Celsius. The vapor pressure of pure water at 25 degrees Celsius is 23.76 torr. So the first thing I'm going to do is I'm going to think of the equation I want to use, which is the same one that I did for example problem 4. We have the solvent and then the vapor pressure of the pure solvent. And then I need to find the moles of my solute and the moles of my solvent. Well, the moles of my solute, I have 35 grams of sodium sulfate. They told me that its molar mass is 142. So that gets me 0.246 moles. Because this is ionic though, I need to multiply that by the number of ions that this thing will produce. How many particles will it produce? And when that goes into solution, it's going to produce 2 sodium ions and a sulfate anion. So 3 total, which means it's going to produce 3 moles of particles for every 1 mole that goes in. So when I multiply that by 3, I get 0.738 moles of solute particles, and that's the number of moles I'm going to use for my solute. So solute particles. I need to do my moles of water, since that's my solvent. I have 175 grams of water. 18 grams is 1 mole. And by dividing that out, we get 9.72 moles of water. So I just go ahead and plug it back in like I did before. The vapor pressure of the solution is going to be equal to the mole fraction of the solvent. So the solvent's water, which means I put water's moles on top. The total number of moles, if I add the 0.738 plus the 9.72, is going to be 10.46. And I multiply that by the vapor pressure of the pure water, which is 23.76 torr. Again, moles cancel. Multiplying all that together, we get, not that, but we get 22.1 torr. And that does make sense with what I said. Initially we have 23.76 torr and my pressure dropped. Didn't drop by a whole lot, but it did drop by some. Okay, ideal and non-ideal solutions. So along with solutions, you can have solutions that act nicely and some that don't. So liquid-liquid solutions that obey Raoult's law, the one we've just been working with, are called ideal solutions. Raoult's law is to solutions what the ideal gas law is to gases. So the ideal gas law, the PV equals nRT, we know that some gases do not obey the ideal gas law, but we pretend like they do. We do the same thing with solutions. Not all solutions are ideal, but we like to pretend that most of them are. So nearly ideal solutions occur when the solute-solute, solvent-solvent, and solute-solvent interactions are very similar. So everything acts nicely because they are all very similar to each other. When they do not obey Raoult's law, these are called non-ideal solutions. And what you're going to see is you get negative deviation and positive deviation. The first one is negative deviation. So if the solvent has a special attraction for the solute, so it really, really likes the solute that you're putting in there, what's going to happen is you're going to get a greater attraction between the solute and solvent molecules. So it's going to be a lot harder for those solvent molecules to escape to the gas phase, which means you'll end up with a lower than expected vapor pressure because you're going to have fewer gas molecules. So this is our pretty ideal solution. Everything's nice and linear. What you'll see though with the negative deviation is that the vapor pressure is lower than expected, and that's because those solute and solvent particles really like each other, so they're staying in solution. They're having a hard time escaping into the gas phase. The same is true then with a positive deviation. If the solute-solvent interactions are weaker than the interactions between the solvent molecules, the vapor pressure will be higher than expected. So it can also cause vapor pressure to increase. So if the solute and solvents do not like each other, they don't have an interaction for each other, it actually causes the vapor pressure to go up, so it's higher than expected. And here's a summary of how you can predict what will be formed in terms of the deviation from Raoult's law. You can look at the interaction between these particles and you can read it, and here's examples of what would happen here. So your ideal is benzene and toluene. They're both nonpolar, they both look alike, they have similar molar masses. So they're going to be an ideal solution. They're not going to be overly attracted to each other. For a negative deviation, it's just going to be a really nice, almost ideal solution. If we do acetone in water, we end up with hydrogen bonding. And hydrogen bonding would be something that would cause a negative deviation. Your expected vapor pressure is what you see is going to be lower than the expected vapor pressure because these two have a greater attraction for each other. And then your positive example is ethanol and hexane. Ethanol is polar, hexane is nonpolar. So because they are unlike each other and they're not going to have an interaction, they're not going to have an attraction for each other, they're going to cause a positive deviation from Raoult's law. And that's the example problem 6 they're asking you about. Which of the following would be ideal, show a positive or show a negative deviation? So if we wanted to look at these, hexane is nonpolar. If we were to draw it out, it's just a chain of 6 carbons with a bunch of hydrogens on it. Chloroform is polar. So nonpolar and polar, those are the ones, because this is nonpolar, polar, this will cause a positive deviation. Ethyl alcohol, hydrogen bonding. We know water does hydrogen bonding, so these guys would have a negative deviation. And then the last one, hexane and octane, both are nonpolar. Both are very close in terms of molar mass, so these would be ideal. They would show you the expected vapor pressure that you would anticipate seeing. Okay, calculations with non-ideal solutions. So not only can we predict what type of vapor pressure we would see, lower, higher, whether it's ideal or not, we can do some calculations where if we put a liquid solute with a liquid solvent, that means both of our components are volatile, we can still calculate the vapor pressure of the solution. And what we do is we just do Raoult's law, except we just have it for A and we have it for B. So we have it for the solute and the solvent. And we're going to do an example problem with one of these. So the solution is prepared by mixing acetone and chloroform. It's at 35 degrees Celsius. This solution has a total vapor pressure of 260 torr. Is this an ideal solution? The vapor pressures of pure acetone and pure chloroform are 35 degrees Celsius. At 35 degrees Celsius are 345 and 293 torr. So what they're telling us then is they're asking us to tell them whether or not this is an ideal solution. So the first thing we need to do then is calculate what is the pressure of the entire solution when I put these together. So again, we're going to just be doing the two different parts as two separate calculations. So I used A to represent acetone. So the mole fraction of acetone times the pure vapor pressure of acetone plus, what's our other one? Chloroform. So the mole fraction of chloroform times the vapor pressure of pure chloroform. If I do both of those calculations and add them up, that'll tell me the total vapor pressure of the solution. So calculating these individually, I can just plug in all at once if I can just know the moles of each of these. So the moles of acetone would be 5.81 grams of acetone, and they gave me the molar mass. 58.1 grams is 1 mole. When I do that, I get 0.100 moles of acetone. The next one I want to do is my moles of chloroform. So the chloroform, let's see, I have 11.9 grams of chloroform. We're just going to leave it at that. They gave me that it's 119.4 grams per 1 mole. And if I do that calculation, comes out at 0.0997 moles. And that's really all I need because everything else was given in the problem. I'm just going to plug in and chug. So the pressure of my solution is equal to, looking in respects to acetone first, will be 0.100 moles of acetone divided by the total, which if I add both those moles up, I get 0.1997. And then up here they told me that acetone's vapor pressure, if it's pure, is 345 torr. Plus, now I do chloroform, 0.0997 moles, still the same total number of moles, but this time my vapor pressure is 293 torr. So if I plug all that in, I end up with 319 torr. So what they told me is that the vapor pressures are there, let's see, this solution has a total vapor pressure of 260. So when we observe it, we get 260 torr. What we expect to get, though, is 319 torr. So this is not ideal. It has a negative deviation from Raoult's law. So the solute and the solvent are having a special attraction for each other that's causing the vapor pressure to drop. Okay, that was it, and we covered a lot of material. So just understanding Raoult's law and understanding the relationship between pressure and how it affects solubility and how temperature affects solubility, and how the structure of things can affect solubility. Those are all really important parts of what we just covered, and we will do more practice with the calculations and talk about this in class.